Alright, today we're going to talk about another one of these early Tesla integrated circuits that have become a staple of this series. The one we're going to talk about today is the MAA725. And what this is a single operational amplifier, and it's all bipolar, I think. So no FETs involved whatsoever. This is a relatively early integrated circuit. This came out in 1973, and it contains 26 transistors. And one of the interesting things is I have a book from the period, and although it's all in German, if you Google translate this, you'll get to, it contains 26 exclamation mark transistors. And it's super cool because apparently that was something worth mentioning. It contains 26 transistors. This must be high tech. This is what makes this really worth doing, is reading this old literature and then you suddenly discover that it says, 26 transistors. Really cutting edge here. Yeah, that's just cool. So, the same book also has a schematic of the innards of this. And you can see there's nothing all too fancy here, although for 73, relatively fancy. We've got the two inputs here, and you can just see they go into a differential amplifier. And I'm not going to go all that much further into it, but the output is here on pin 6. And we've got this complementary stage here that is going to allow us to swing between this pin here and this pin here, or at least close to it. So the pin 5 down here is actually frequency compensation output or input. And there should be another pin here that is on the actual Tesla datasheet, but not in this one for some reason. Where you can actually connect a potentiometer to, I think, set the offset to 0. Which a lot of these early operational amplifiers have. A lot of the later quad op amps in a single package just don't have that. I imagine because first of all, it saves on pins, and second of all, the offsets have gotten a lot lower these days. So, what else can we say about this? The maximum voltage swing, or the maximum supply voltage is plus minus 15 volts. Okay, that's pretty unimpressive. That's just a normal operating range for an op amp. Although today you get op amps that can go much, much higher, and I imagine they existed back then. Especially vacuum tube op amps. Yeah, obviously got a lot more there. The offset is 1 millivolt, it says here in my notes. And I've got amplification of around 60 dB if you don't put a resistor in to limit the thing. So it's actually a fairly capable op amp, this. And this is just my paintbrush that I used to point at things. So it's actually a pretty cool op amp. It's definitely still usable. I mean, if you can still use a 709 in 2021, you can definitely still use this. So as usual for this series, I have a demo circuit on this little board here, which as the series continues, starts to look more and more oxidized. But not to worry, circuit still works. So we've got our operational amplifier here, and the only connection we have at the moment is we have pin 2, which is the inverting input, hooked up to the output on pin 6. So what we're going to do here is a simple voltage follower. And what we have to hook up now is the remaining components. So we need to put a power supply on there. We need to have some sort of input signal, and then we should also hook up an oscilloscope so we can see what's going on. Right, so we've got our positive input, our positive supply voltage. Then I'm going to hook up to pin 7 here. Then I've got negative, which is confusingly also red. And then I'm going to hook up to pin 4. And then the ground lead from the power supply goes just on this ground here. So I'm going to supply this with plus minus 6 volts, just because that's what I have handy here. But that should definitely work. So this is the negative from the signal generator, and this is the positive from the signal generator, and that we're going to hook up to the non-inverting input. Right, so the output is connected to the inverting input, here pin 2, and then we're going to hook up this to the non-inverting input. So last thing that we're still missing is our 2 oscilloscopes. Oscilloscope probes as usual, and I'm going to hook up channel 1 to the input here. You can just see what signal we're putting in, and then we're going to hook up channel 2, which is the purple, to the output, so you can see what's coming out of this little circuit here. Alright, so there we are. Now I'm going to switch the camera over to the oscilloscope, and I'm going to switch everything on, and then we can see what this does. Alright, if we have a look at the oscilloscope here, we can see that our non-inverting amplifier with a gain of 1 is doing what it's supposed to do. This upper trace here is the input, and this lower one here is the output. And at the moment we're going at a leisurely 58 Hertz. Got it set to about 60 on frequency generator, and yeah, that's what we're getting. So if I switch this to a square wave, and I should probably turn this down a little bit, I actually see that these reproducing it as distorted as my signal generator is producing it. But if we turn this up a little bit, actually see this is at 200 Hertz. It's still doing reasonably well. And in this demo I left the frequency compensation and the asymmetry correction, left all of that open, which is probably not great, but I thought for a quick demo it should work. What you can see is that this square here, it's definitely not a square down here. Square waves are one of the hardest things to reproduce, because you basically need infinite gain in voltage between here and here. Because if you have a perfect square wave, it is at 0 here, and then in the next instant it's up there, and you have no rise time whatsoever. This is obviously relatively hard to do. So let's see what we can do at a couple kilohertz. Let's try 170 kilohertz. It's still doing reasonably well, I think. I think we lost a little gain here. That's still doing okay. Just switch it up to 100. Yeah, it's still doing okay. So obviously, you could just look at the data sheet to find out what this can do. But this is just, we're having a little fun here, playing around with it. Switch this back to a sine wave. Yeah, that's looking a lot worse. Yeah, that's not looking great. But yeah, anyway, this was just a quick look at this reasonably early operational amplifier by Tesla. And I think on the next video, I'd like to stick with these Tesla chips for a little while longer, and do some more about the transistor arrays. And then maybe also talk about some Western transistor arrays that were around at the same time. But after that, I think I want to leave the 70s for a while, and we're going to look at something that is, I think, really interesting. I have a couple examples of cloned microprocessors from the 80s, and I think that would be a fascinating topic too. Some of them have actual home computers that they were employed in. So I think this is going to be an interesting couple of videos. But I'd like to do a little more 70s stuff before we leave for the 80s. And I think I'll also rename the series then, because it's not really early integrated circuits anymore. Although I haven't really come up with something better. It's not modern integrated circuits. And not quite as early integrated circuits. Doesn't sound very, very good as a serious name. So, yeah, if you have a better name, leave it in the comments. And as always, I thank you for watching this, and I'd really like to see you on the next video.